Okay, so lecture 2 in linear algebra is about reduced augmented matrices. So we'll talk about vector notation a little bit, algebra vectors, and then reduced augmented matrices, square coefficients, more rows than columns, more columns than rows, and summary. So notation for vectors, V is V1, V2, V3. Often we'll put a little arrow over a vector or write a boldface to indicate that's a vector. The numbers V1, V2, V3 are the components. Vectors can also sometimes be written as a horizontal line. You have to be careful about whether this is a point or a vector sometimes. So what can we do with vectors? You can add them, you can multiply them by real numbers, you can reduce complicated ones to simpler ones. So how do we add two vectors or subtract them? Here's two vectors, for example. You can add them. 1 plus 4 is 5. 2 minus 5 is minus 3. 3 plus 6 is 9. So you just add the components together. If we take a vector and we multiply it by a number, like by 2, the number 2 distributes to each component. So that becomes 2, 4, 6. You can also do that in the opposite direction, right? If we have a vector, say 10 minus 6, 4, and you see that 2 is a common factor for each of these things, you can factor out a 2 from each one, and you get 5 minus 3, 2. So the key thing to remember about multiplication by a number or factoring something out is it needs the number, when it gets multiplied in, multiplies to everything. When you factor something out, it has to be common to each term. We can also, if you have sort of more complicated vectors, suppose we have a vector that's 3 plus t, where t is some number times 5, 2 minus t, and t. All right, we can split that apart because there's a plus and a minus and a 0 plus t there. So you can split that into a part that's got 3, 2, 0 plus 5 times t minus t, t. And then you can factor out the t to get 3, 2, 0 plus t times 5 minus 1, 1. And we'll see that form for solutions to systems equations several times. So if you have a complicated thing that's got some pluses and minuses and a parameter t, then you can rewrite it as sort of two simpler vectors, this vector plus that vector times t. Okay, so reduced augmented matrices with a square coefficient matrix. And the question is, if you have a system of equations with a square coefficient matrix, what are the possibilities for the reduced augmented matrix? So if we have this augmented matrix, remember I should put a line here because this is the coefficients and these are the solutions. And this system of equations would be rewritten as, this is my x1 column, my x2 column, my x3 column. So it'd be a11 x1 plus a12 x2 plus a13 x3 equals b1. And the way the coefficients are written, the first subscript tells you which row it's in. These are all from the first row. And the second coefficient tells you which column it's in. Column 1, column 2, column 3. So the second equation we're dealing with is a21 x1 plus a22 x2 plus a23 x3 equals b2, and then a31 x1 plus a32 x2 plus a33 x3 equals B3. So this augmented matrix corresponds to this system of equations. This is a collection of 3 equations in 3 unknowns, and so we have that our matrix for the coefficients is what's called a square matrix. We have 3 rows and 3 columns. So if you reduce it, if you go through the reduction process, what can possibly happen? So one option is that after you do all the reduction, you get rid of the A21 and the A31 terms to get zeros there. And then use this number to get rid of both of these 2 terms. So you can get zeros here and here. And then finally, you can use this term to get rid of these 2 terms, and you get zeros here and here. And that's the best case, because that system of equations is just that, and that tells you what the solution is. There's only one solution. Right? And the D1, D2, D3, they're whatever numbers you get left after doing all the reductions from B1, B2, and B3. Okay, so there's a unique solution if everything cancels out nicely. What can also happen is that you end up with the bottom row having its coefficients be getting canceled out by one of the previous rows, and that happens occasionally. So here there's 2 possibilities. The first is that D3 does not equal to 0. That means you have no solutions. And why is that? Well, if you write this out as a system of equations, what do you get? You get x1 plus c1 x3 equals d1, x2 plus c2 x3 equals d2. That's the first 2 equations. And then you get 0 equals d3. And if this isn't 0, right, that's a contradiction. So if you get a row of zeros in the coefficient matrix, you better get a 0 over in the solution, because if you don't, then you get no solution. And then if D3 does equal 0, you have infinitely many solutions. Because then our equations are x1 plus c1 x3 equals d1, x2 plus c2 x3 equals d2, and then 0 equals 0. That's the third equation. If d3 is equal to 0, we can ignore that one. What we'll do is we'll solve these for, what we'll do first is we'll set x3 to be equal to t, and t is called a parameter. And then our equations become x1 equals d1 minus c1 x3, x2 equals d2 minus c2 x3. So we solve those 2 equations for x1 and x2, and then finally x1 equals d1 minus c1 t, x2 equals d2 minus c2 t, and x3 equals t. And then very finally, we can write these as vectors. The solution vector is x1, x2, x3 equals d1 minus c1t, d2 minus c2t, t. And then like we did above, we can split that, don't set a fraction, d1, d2, 0, minus So we'll take the d1, d2 out as one vector, and then we'll factor out a minus t. And then we're left with c1, c2, minus 1. All right, so we get two vectors, this one, and the second one is multiplied by this parameter t. So one thing to note here is that at least one of these two has to be non-zero. Because if you start with numbers in a column, you can't reduce it in a way so that all the numbers disappear. You always end up with at least one number in the column, one non-zero number, right? So if you actually have a third variable, right? So there's a coefficient on one of the third variables, you're going to keep the coefficients. Okay. So what's the other possible case? The other possible case is this, where you've got a C1 here, and like I just said, this C1 can't be equal to 0 because otherwise there would be no, this entire column would be 0 and x2 wouldn't show up at all. And then we have d1, d2, and d3. So here our solutions look like the equations look like this. Right, so if we take these system of equations, remember that's my x1 column, x2 column, x3 column, I get these three equations. From this one, we know that d3 equals 0 means not equal to 0 means no solutions at all. If d3 does equal 0, then x1 equals d1 minus c1 x2. So this term over to the right side, that'll turn out to be the term that involves the parameter, and x3 equals d2. So we parameterize this, we set x2, right, which is the one that corresponds to the c1 equal to t. And then what do we get? We get x1 equals d1 minus c1t. x2, well, we set x2 equal to t, and then x3 equals to whatever the constant d2 is, because that's that equation. And in vector form, this becomes the vector, the solution vector x1, x2, x3 is d1, 0, d2 minus t times c1, x2 is t. There's a minus one there because this is a positive t and we get a minus minus, and then 0. And so same kind of setup that we had before. We have a vector and then a parameter times another vector. And the very last case would be this, where we can actually get rid of this, and C1 can't be 0 and C2 can't be 0 because otherwise you wouldn't have x1 and x2. So if your coefficient matrix has a row of zeros, to have any kind of solution, you need those two to be equal to 0. So no solution if either is not 0. How can we read off the solutions to this? Well, this will get a parameter, and this will get a parameter. So the equations then, if d2 and d3 are both equal to 0, is x1 plus c1 x2 plus c2 x3 equals d1. And then 0 equals 0, and 0 equals 0 for d2, d3 equals 0. So x1 equals d1 minus c1, x2 minus c2, x3. We'll set x2 equal to s and x3 equal to t because they're different numbers. And And so then in vector form, my solution becomes x1, x2, x3 equals the constant term, which is d1, and then no constant terms for x2 or x3, minus the first parameter. So x2 we're calling s. So x1 has a minus s, a c1, minus 1, 0, and then minus t, c2, 0, minus 1. Right? Because in terms of s and t, x1 becomes e1 minus c1s minus c2t. So infinitely many solutions, because if you actually knew what the numbers were, any choice you make of s and t gives you a new solution. So you can read off, if you know what the shape of the reduced matrix is, you can read off what types of solutions you get by playing with the reduced matrix. So suppose we have this situation. So our coefficient matrix, we've got more equations than we do variables. So this is the equations a1 x1, a11 x1 plus a12 x2 equals b1, a21 x1 plus a22 x2 equals b2, and then a31 x1 plus a32 x2 equals b3, right? So I've got 3 equations, 2 unknowns. Generally, we'll have more solutions. We'll have infinitely many solutions here because, no. Generally, we won't have any solutions because we've got too many constraints and not enough variables. So the best case is if you do this and you can get zeros in the bottom. So we can use this number to clear out these two. And then once we have this one, we can use that number to clear out this one, and that gives us this. So if D3 does not equal 0, there's no solutions. And that's sort of the most common thing to have happen. If D3 equals 0, then x1 equals D1, x2 equals D2, and x3 will be a parameter because we have no constraints. Oh, I don't have an x3, sorry. If D3 equals 0, there's no solutions. If D3 does not equal 0, there's no solutions. If D3 does equal 0, then x1 is D1 and x2 is D2, and we're done. The other possibility is this case, where in the process of clearing out the first column, we also accidentally clear out the second column, and we end up in that case. And here we have x1 plus c1 x2 equals d1, and then 0 equals d2, and 0 equals d3. So if these are not both 0, that means we have no solution. If they are both 0, then we do have a solution. We set x2 equal to a parameter. And rewrite the solution as a in vector form. So if you've got more rows than columns, that means you've got more equations than unknowns. And that means when you do your reduction, you'll always end up with a row of zeros in your reduced matrix. And then you just have to hope that the corresponding entry in the solution column is also 0. If it's not, then you have no solution. More columns and rows, then what's the possibility? So if we have this corresponds to the set of equations. I'll just mark off the thing. We get a11 x1 plus a12 x2 plus A13 x3 equals B1. Part of linear algebra is sort of looking at a matrix and saying, okay, I can sort of understand what set of equations that corresponds to. And so a little bit of practice and writing it down is not unwarranted. So I've got 3 variables and 2 equations. So what happens there? Well, when we try and reduce it, we can use the A11 to get rid of the A21, and then we can use the A22 to get rid of the A12. But if these, we can't get rid of these, right? At least one of them is going to stay. So unless in the process of solving, clearing out A11, clearing out the A21, all 3 of these just sort of get canceled out. So, but the point is we'll always end up with at least one non-zero number in the 3rd column and in the 2nd column and the 1st column. So this solutions, right? X1 plus C1, X2 equals D1, X2 plus C2, oh, sorry, that should be an X3, X3 equals D2. And that can be rewritten where we make X3 equal to a parameter T, and then X1 equals D1 minus C1 T, X2 equals D2 minus C2 T, X3 equals T. So every choice of T gives you solutions, and we have infinitely many solutions. And it doesn't matter what D1 and D2 are. Same thing for this, we will get infinitely many solutions, because this is X1 plus C1, X2 equals D1, X3 equals D2, and set X2 equal to T to be the parameter, and you get infinitely many solutions. This is the case where you might not get solutions, right? A row of zeros and something in the solution column need D2 not equal to 0 to get any solutions. If D2 equals 0, then 2 parameters, because we have 2 columns where we don't have a leading one. So if D2 equals 0, the equations we get are X1 plus C1 X2 plus C2 X3 equals D1, and 0 equals 0. So then we'll set X2 equal to T, X3 equal to S. Those are my 2 parameters, one for X2 and one for X3. And then X1 equals D1 minus C1T minus C2F. And there's our solution. We can write it as a vector. Well, we have 2 parameters there. Okay. If the image vector is 0, so suppose D1 and D2 is 0, always. Well, if D1 and D2 is 0, then they're always going to be 0, because when we do the row reductions, you're always just adding and subtracting things. So if you start out with these 2 equal to 0, then they're always going to be 0, right? And so if B1 and B2 start out to be 0, then D1 and D2 are going to be 0. So same thing all the way through here. So if you start with zeros, so this is saying that your solution, say B1, B2, B3, is equal to the 0 vector, which is just 0, 0, 0. So the B1s are the numbers you start with, the Ds are the numbers you end with. And if you try to make equal to 0, then there's always at least one solution. Just make all your variables equal to 0, and that'll give you the solution. So a fully reduced augmented matrix has these problems. All rows of zeros at the bottom, because you can move rows. First non-zero number in a row in the coefficient matrix is 1, called the leading one, and there's only one leading one in any column, and I forgot the fourth one. Every column has at least one non-zero number, right? So when we look at these reduced matrices, right, you could have a row of 0 at the bottom in the coefficient matrix, and then this is a leading one, and that's a leading one. This is a leading one. Leading one can shelter parameters as you go left to right, but then there have to be rows of zeros. So another reduced augmented matrix is I have a leading one here and 2 rows of 0 at the bottom, and the leading one hides or shelters these two numbers, which turn out to be parameters. Okay. So how many solutions are there? There are either 0, there's 1, or there's infinity, right? Because if everything works out nicely, you get exactly one solution. If you get a row of zeros equal to a non-zero number, then you have no solution. And if you end up with a parameter, you have infinitely many solutions. Generally, we are interested in square coefficient matrices, where the number of rows is equal to the number of columns, right? You have the same number of equations as it does variables, and that kind of a situation, generally you will have exactly one solution. Okay, so that's that for now.